Okay, laptop camera is being weird. Let's try turning off the light. Is this visible? Hopefully this is visible. Something. Why is this still here? How do I pause the video until everything's ready? Hi, can you see the difference? Can you see the difference in the quality of the... Actually, new idea. The forbidden jutsu of opening up a window? That's visible enough. Alright. Oh my, why is it moving? I tightened this already. Did I not tighten you? You're not supposed to move. Is it still fine? This marker is too skinny. Said every morbidly obese relative I've ever had. Alright, we're gonna fix it in post. It's just gonna be fixed in post. We'll up the contrast or something, I don't know. But if I up the contrast, would that window be doing a disservice? Because for some reason it's flipped. I don't know. It's fine. So this is the combinatorics book that I have. It seems lovely so far. It's a walkthrough combinatorics. I don't know why it's all flipped. We're going to need to mirror it in post or something. Who's we? I'm doing this. Let's see, the book is... I can't flip the pages. The book seems to be... How about I look at this? The summary of it is... This is an introductory combinatorics course lasting 1 or 2 semesters, an extensive list of problems ranging from routine exercises, blah, 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 blah. This does not actually capture... That just looks like a mugshot. That's just a mugshot of the author. I don't know what he did. Blah, blah, blah. Are we sure he didn't touch little boys or girls or something? I can't tell. I don't like seeing the author. He just looks creepy. Why is it just straight up a mugshot? Well, I suppose it's not straight up a mugshot because you need the little lines on it. But first off, this is what... where's my dog? Coop. Coop. You're back there. Everything's fine. So... First off, this is what I was going to do. So the pigeonhole principle goes, let's see, make sure I don't confuse N and K for later. Bot bing, bot boom. I didn't go over the vibe of it. Alright, so the pigeonhole principle is... God, this book is hard to hold. Let N and K be positive integers. So, let N and K be pos... that's spelled wrong, I feel. I feel positive is just wrong. Positive. That's not an I. Integers. Okay, n is greater than k. With n strictly greater than k. That k looks weird. There we go. Is that still visible? And it seems visible enough. Lovely. And suppose we have n identical balls and k identical boxes, then there will be at least one box in which we place at least two balls. I'm going to change the phrasing of that because B and B is annoying. Where am I going to put you? Ah! Did I increase the title? The cover? Mildly, but it's mine. If we place n objects, we'll call this balls, it's fine. N balls in k containers, then there will be I could probably pause this. There we go. So the pigeonhole principle is let n and k be positive integers with n being strictly greater than k. If we place n balls in k containers, then there will be at least one container with at least two balls. Now, here's what I was going to do. Because whenever you read a theorem, the first thing you think about is, alright, how am I going to prove this? Or how would I prove this? So I was going to do as follows. I was going to take an approach, a direct approach, where we try to actually place the balls in the containers. So, for example, suppose we have 3 containers and 4 balls. That's wrong. It's wrong. Why is it always tilted? Stop being... Okay, so we have 3 containers and we have 4 balls. And we're going to try to actually place the balls in the containers. Now, we note that why is it so bright now? I swear it wasn't this bright earlier. There we go. Now, we note that the way we actually distribute them doesn't matter very much. So this is a kind of a without loss of generality type thing, where we try to put each ball in the container in order, where there are 3 containers, and we put it in the container and we put the ball, which are labeled, but the labeling doesn't actually matter. We note that none of this actually matters when we're trying to put it in the container. Where the number of containers mod the ball it is the container we're going to try to place it in. So 0, so for this k equals 3 and the number of balls is 4. So 0, we're going to try to place this ball. 0 mod, that's terrible. 0 mod 3 equals 0. Or I should say equivalent is equivalent to 0. Why is this slanted? Stop that. Okay, 0 mod 3 gets placed into, is equivalent to 0, so it gets placed into the 0th container. And we do this all the way up to the one that, the one, the most one, the one where the ball which we have not placed, which we are trying to place now. So we're on 3. 3 is greater than 2. However, when we do 3 mod 3, we get 0. So we place it in the 0th container. However, we know that the 0th container already contains a ball. And so at least one of them has, at least one container has more than one ball in it. Now I'm going to actually write out that proof. But that's the intuition behind it. Okay, here's my argument. So we start the proof by saying, know that the way in which we place the K balls does not affect the following argument. Only the placement of the final ball. Labeling and methodology are purely for convenience. Which that part is self-explanatory. We're saying it doesn't matter how we place them. And there is actually a way we could say that a bit more. We could structure this proof in which this is implicit. And I'll get to that after the actual proof. So let there be K containers labeled C0, C1, all the way up to CK minus 1. And N balls labeled B0, B1, all the way up to Bn minus 1. Going in order, that is replacing B0, then B1, then ... all the way up to Bn minus 1. Going in order, place B sub I in C sub j if, let's see, I mod k is equivalent to j, which is simply what we did before with the particular example. This means we must place B sub k in C0. However, B0 at this point is already in C0, so the proposition is true. Now, the way which I came up with while writing this proof, which I think is interesting to implicitly say this, is to interpret this more as a graph, where isomorphisms are commonplace. So we would have some top vertices. This is not a great place to go. You're going to need to stay here. Okay, so let's actually move this over. Alright, so blue is going to be our containers, not our containers. Blue is going to be our balls, and brown is going to be our containers. So suppose we want to make a graph. We want to graph this out. And obviously, if we're going to make any kind of attempt at putting each ball in a unique container, we're going to need to do this. Otherwise, we do something like this, which is stupid. And we're not stupid. At least not entirely, so we're not going to do that. And now, we have a graph in which no matter where we place this final ball, no matter which edge we draw this, no matter which vertex we join this final ball to, is going to be isomorphic to any other one. And that's a way we could implicitly say this without kind of getting into some dodgy territory, which I think is really cool, because you wouldn't normally think of graphing this problem, but it does seem to actually be a viable solution, and it does handle this kind of argument really well. Anyways, let's get on to the book's proof. So the way the book proves it is much more elegant, in my opinion. Even if, after the graph argument, I do really like my proof for it, even though I didn't put the graph argument in my proof. I came up with that after the fact to handle some potential criticism. But it goes practically in the following. Wow, why is it so overexposed? Yo, stop. Jesus. I forget what I was saying. So the way the book does this is it assumes the contrary. So that is to say, suppose that we have this and this, but every container has exactly one ball in it. And why does it keep overexposing? Jesus Christ, stop doing that. Okay, it seems fine. At least for now. So, let me see what to do. And we're going to do. Alright, assume there is no box with at least two balls. So, that's a W and not a U. Ass. Did I spell assume correctly? I did. Now it's correct. So it says, assume there are no boxes with at least two balls. Or assume there is no box with at least two balls. And here we're taking box to mean container. So that means that every box has 1 or 2 balls in it. Is means completely on there? Yes. Not 1 or 2, 1 or 0. That's a terrible A. It looks like the Green Goblin. That 0 isn't round enough. So, this means every box has 0 or 1 ball. So then goes denote M to be the number of boxes with 0 balls in them. Wait, no, is that sorry? Greater than or equal to 0 balls in them. Wait, what? No. Yes, that is what that says. Then goes let M be the number of boxes with 0 balls. So then goes, however, this means the total number of balls, assuming they've all been placed, which this proof is implicitly doing, however, this means the number of balls, K, equals K minus M which is less than or equal to K, which is strictly less than N. So we have the number of balls is strictly less than the number of balls, which is a contradiction. Then and I think this proof is much simpler, much simpler, because it doesn't need to be reworked using an entirely different framework, and it's just nice. It's a nice proof. Nice, simple contradiction proof. But anyways, I do think the direct approach, at least my direct approach, is very cool. But this is lovely. And being that it's the first proof that we see, that's a sign for good things to come, hopefully. Again, this is a walkthrough combinatorics by, there's an accent over the O, Mikolos Bona? Mikolos Bona? It's that guy. And it's very nice. Hope you enjoyed.